but I'll do my best. So, can everybody see the slides? Cool. Okay, I'm gonna start. So this talk is gonna be C++ 11 and 14 at scale, what have we learned? And it's basically a talk that covers a bit of experience that I have with teaching and the way I teach things at Bloomberg, because there I am a technical trainer and a software engineer. Also a bit of self-advertisement for the book that I've written with John Lagos and other people. I'm going to talk about that in the talk. And then at the end, there's going to be a case study from one of the things that we cover in the book, and it's going to be about friendship. So if you like friendship in C++, and if you don't like it, that's going to be interesting. A little bit of backstory. So about me, my name is Vittorio, and I currently work at Bloomberg as a technical trainer and software engineer. I joined the company in 2016 in London, and I joined as a software engineer there. And life was good. I went through the training, C++ training, and it was pretty good. But I noticed that there was something missing. We were being taught just a little bit of modern C++, but mostly was C++03, and the reason was that Bloomberg had a lot of code running on legacy architectures on Sun and IBM machines, and at that time, it was quite common to end up working on a machine or a project where the exposure to modern C++ was limited. But I also joined at the same time where the company was migrating to mostly Linux-based architectures, so I saw a perfect opportunities to actually teach people 11 and 14. It started as a simple 1-hour talk, like an overview of what's new in C++. People loved it, and then from there it kind of snowballed into a 3-day course that I'm giving still to this day with very high, attendance, and people really like it and they get interested in C++ 7 and 14. I'm also giving a 17 one now and working towards the 20s. And it started as something like a little bit for fun, but it became my primary job, and I'm happy about that. At the same time, around 2018, I was at C++ Now, which is a fantastic conference, the one in Aspen. If you haven't been there, I strongly recommend it. I really missed it this year, being there in the mountains and enjoying the weird feeling of being isolated from the rest of the world in this beautiful scenery with C++ experts is something unmatched. But anyway, 2018, I was walking towards the talks with my coworker and friend John Lagos, and we were talking about my experience at Bloomberg, what I've been doing. He actually attended the 11 and 14 course, and he told me, look, this is nice, you have something good here, why don't we make a book about it? And I was like, yeah, there's a lot of books about 11 and 14, so what are we gonna do that's unique and it's gonna bring something new to the table? Then we talked about it a little bit, and we realized that there's really nothing that analyzes 11 and 14 from the perspective of a large corporation and sees, what has worked, what didn't work. Most of the resources we found were either covering, the basic syntax and telling you, oh, this is this feature, these are some examples, and this is what can go wrong and what works. But they never really analyzed the consequences of a long time usage of that feature in a real company. So we tried to look at that perspective and see what the consequences were at Bloomberg, in other companies. We talked to a lot of people, got a lot of horror stories and good stories. And in the end, I feel like that from 2018 and 2021, my life has been about rediscovering 11 and 14. So why, almost 10 years later, why was I doing this? And the reason was, it's easy to grasp the basics and the ideas that 11 introduced, but you need the time and experience to actually see the consequences of those things at scale. And, by seeing what happened at Bloomberg and talking to people, other companies, we really got a lot of interesting information, and we managed to get a deep analysis of these things. 2021, we finally released this book. It's written by me, John Lagos, Rostislav Kladnikov, and Alistair Meredith, all people at Bloomberg, and a lot of contributors. I'm going to name them later, but people from the ISO committee and rock stars like Alexandrescu or Sean Parent. So there's a lot of different point of views and perspectives in here that provide a very deep and thorough analysis. So this is available for pre-order right now. I'm going to give you some links later, and it will be out in December. Okay. Enough advertisement. Let's talk about what I'm going to talk about. So first of all, why are we still discussing 11 and 14 in 2021? What's the point? Isn't it a bit late to talk about them? And then I'm going to show you how 11 and 14 can surprise you today, even if you have used them before for 10 years. Then we're going to discuss what it means to write C++ at scale and how that changes the way you might teach it or the way you might approach it. We're going to talk about the idea of the safety of a feature, which is this concept we introduced in our book, which is a bit controversially named on purpose, but I think it gets the points across well. And then at the end, we're going to have a case study from something from the book, and we're going to take a look at extended thread declarations, what they do, where they shine, and what problems they cause. Okay, so the first thing is, why do we care about 11 and 14 almost 10 years later? There's something that isocpp.org does every year, which I find really useful, and it's basically a survey that they send out to C++ developers, and they ask a lot of questions regarding, their tooling usage, what kind of domain they work in. But one of the questions they ask is, what kind of C++ standard are you allowed to use at work or for hobby projects? So we can see that in 2018, these were the results, and I'm just gonna synthesize them here. The full 11 adoption was around 83%, and C++ 14 adoption only around 58%. Things gradually get better, 88 and 65 in 2019, 90 and 74 in 2020, and 2021 we get to 87% and 67%. So things have been going steadily up, and you can also see, C++ 17 becoming more prominent and some people experimenting with 20. But if you think about it, even though these results seem good, in 2018, which is 7 years after the release of the standard C++ 11, modern standard, around 20% of the people were not fully using it, which is quite a lot considering that it's 7 years after it was released. And in 2021, around 25% of people are not fully using C++ 14. Sample size, of course, matters. It has decreased a bit and went back to 2021, and in general, there's always a bias because it's a survey that's being filled by people who visit those websites. But to be honest, since it's a survey that's being filled by people that are interested in C++, the real world is actually worse. And in fact, personal experience, both at Bloomberg and talking to people with other companies, tell me that even nowadays, 11 is still a luxury in some places, which is really unfortunate. But there are good reasons for that. One of them might be legacy architectures and old code that cannot run on modern architectures, but also bad reasons such as, lack of interest or the management just not caring about these things or people just not being aware of them. And I see people complaining online all the time. I don't know if that's a vocal minority, but the truth is, even nowadays, C++ 7 and 14 might be a luxury for some. Another thing that I want to point out is the book that we wrote is not just aimed to teach 11 and 14 to people that have not been exposed to it, but also if you feel yourself, quite familiar with 11 and 14, this book is going to give you an analysis which comes from, time and experience. And what I mean by that is, imagine researching the impact and the consequences of these features throughout multiple years at a large-scale company. What have we learned? What actually works? Because, if you're making your hobby project, for example, I like to experiment a lot with, bleeding-edge modern C++ features. But at a large company, maybe something that has worked really well for you, or maybe for your team of 5 people, then it might not scale the same way. I'm going to monitor the chat. If you want to unmute yourself and ask questions as well, that's fine. I like to keep things interactive. I got a question here. I will reply later to that one because I think we're going to cover it as part of the talk. So what I was saying is basically, it's you've heard this before, but experience is the best teacher. And I've been using Modern C++ since around 2012, both for hobby projects, for my own personal things, and also at work. And at Bloomberg specifically, 11 and 14 have been very widely used in production over the past 6 years, and I've been teaching them professionally over the past 4 years. What we noticed is that there are great learning resources. You can go on Google, you can buy books. They teach the features. They teach why they exist. They teach how to use them, but they don't teach the experience. It's something that is hard to teach, but this is what we're trying with the book. We're trying to actually get that experience into a format where rather than having you go through 5 years of using it, you can understand what has worked for us, what hasn't worked for us, and try to avoid our mistakes and replicate what went well. And in general, what looks good on paper might not work in the real world. It's easy to, create a guideline, but that, could work for a team of 5 people, for a small project, but maybe that guideline might not apply to a company which is a bit larger. So how can 11 and 14 surprise you today? In general, there are a lot of edge cases and a lot of interesting things that have been discussed in the past, but either many people don't know about them, and maybe this talk is going to be, we're going to see how many people, know a bunch of stuff here. But also, even after using 11 and 14 for years, there are weird corners of these features that pop up from time to time and are unexpected. So I'm just going to play around and I'm going to ask you, what do you think is the smallest change to the core language in C++ 11? So the smallest possible thing you can think of. Any ideas? Core language, not library.
Maybe that anonymous namespaces are defines static functions, like they have internal linkage now. That's something new in C++ 11.
Anything that has to do with linkage is probably not small. Like, think very small.
Yeah.
Think about syntax.
Oh, what about not needing spaces between angle brackets?
Yes, exactly.
Yeah,
So that's it. So yeah, it's a very tiny thing, right? It's silly because we have to put a space here, and the compiler would tell us, hey, I know you want to close templates, but you have to put a space there. So the compiler actually knew what we were doing, but it wasn't allowed to parse it that way, which was pretty annoying. So in 11, they actually made it possible. And this seems super innocent, but even a small change like this one can have impact. It could make a valid C++3 program ill-formed in 11. Or you could write a single program whose behavior is different at runtime, depending on whether you compile it under 03 or 11. So as an example here, for the first point, if I have this padded buffer struct, takes a int as a template parameter power of 2, then I can write this in C++3, because C++3 always interprets the double angle bracket as a shift operator. And this will compile and work in 03, but in 11, this will be ill-formed. Of course, the fix is quite easy. You just wrap this in parentheses, and it works. Not a big deal, but I'm just trying to show you even the most inconsequential thing can actually matter sometimes. Even worse, I'm not going to stop and explain this example, but basically you can craft, as I mentioned, some sort of program that by doing some weird stuff with idioms and scope resolution operators and shift operators and things like that, depending on the compilation of this program, whether you use C++3 mode or 11, it will return either 100 or 0. So I'm not trying to say that this is something that can happen in practice very often. It's very rare, it's very weird, but just humor me. I'm trying to prove a point. Even a tiny change that seems inconsequential can actually cause issues. Butterfly effect, right? And this is probably not a very realistic example, but there are things in the language that are more impactful and that you might not expect. So this is just an example of something innocent hiding a pitfall. And as I mentioned, this is quite, slight code. But how about attributes that can actually make your code ill-formed NDR? If you don't know what that means, it means ill-formed, not diagnostic required, which means your program is completely broken and the compiler will not tell you. And attributes can do this. Like, attributes are supposed to be annotations. How can they make your program broken? That's weird, right? Extern template. Every time I hear about extern template, people think that it's designed to improve your compilation time or code size. But actually, sometimes using it can do the opposite. And it's kind of weird, right? And there are actually some use cases for extern template which are very counterintuitive. Like, when you use it in the way that you think it should improve things, it actually makes them worse. Meyer singleton, which is basically the idea of using the new guarantee regarding static initialization of variables that is now thread safe. It's a very nice way of creating singletons and without having to write any boilerplate. But have you ever thought about the destruction order of these things? What happened? Can you ever get into undefined behavior with something that seems super simple and impossible to get wrong? And the answer is yes. Rostering literals. They are super nice. You can embed your thing in there. Looks perfect. You don't have to escape anything. What about the white space? What happens if you save your source file with a certain encoding? What happens if you use Unix line endings or Windows line endings, can that cause problems? And the answer again is yes. Your program might be different depending on the editor you use or the platform you're reading the source code on. So point here being, almost every feature has a dark side. Even the ones that are very innocent and simple actually can hide some pitfalls, and it's unlikely you'll find them very often, but when you find them, it's best if you are prepared for them, and it's best if you know how to avoid them in the first place. Okay. The other thing that I think is interesting regarding the book and teaching in general is scale. And teaching C++ 11 and 14 to hundreds of employees is challenging, not just because of the sheer number, but because there is a lot of diversity in terms of skill and seniority that I get in my classes. And also, the other problem is we have a style guide, we have guidelines, and sometimes these guidelines might seem weird or might seem outdated. And sometimes they might actually make things worse or better, but who is actually responsible for the style guides? Who is the person that is writing them, and who is reviewing them, and what is their source? Like, is it just opinion? So one of the things we're also trying to do with the book is have some sort of objective analysis of every single feature. We are not really giving any recommendation, but if you were somebody that's responsible for writing or maintaining a style guide or a set of guidelines, you could look at our book, see exactly what things could go wrong with certain features and what is the risk-reward ratio, and then based on that, you can write your style guide. In terms of diversity, I've had students and employees that range from an age of 21 to 70 plus. I've had people with a lot of prior C++ experience, and I've had people that was the first day writing C++. I've had people with C experience, which is arguably worse than people without C++ experience. I've had people with a lot of prior developer experience. Maybe they haven't really done C++, but they've been in other big companies. And I've had people coming just from university. I've had people experience with other languages. The Haskell people that want to do things in the Haskell way. The Java people that unfortunately want to do things in the Java way. And people that are interested in modern C++, they are excited. They're like, yeah, I want to use all this stuff. I find it cool. And maybe that excitement is positive, but also negative because they might overuse things. And people that just don't care. They just want to work, get paid, and go home. So they're like, if I want to teach you auto, I have to tell you why it's going to make you a better developer and make you, work less. Not that it's cool, right? And people that are going to end up writing application code all their lives, and people that want to go into library development. Like, the diversity of people that I have to teach is huge, and being able to prioritize and figure out what I should teach is really important, and it always changes. I always try to make the courses better for everybody, but it's really hard because of the diversity. The other thing about style guide, I mentioned this before, but yeah, what is the input to a style guide? And this is something that also we want to address. Another point I want to make here is that there are companies like, for example, Google. They have really fancy and powerful code governance tool. Like, they can query their entire company code bases. They can figure out if there's something that needs to be changed. And if they want to make a change to the style guide, they can literally send a PR to update the entire code base to reflect that change. In other companies, this luxury is not available, maybe because of the way that the code is stored, maybe because the tooling is not there. And a style guide in those companies is kind of essential to promote consistency and discoverability, and it's also a little bit harder to change. So depending on what your company does, again, people might rely on style guides and guidelines more than other companies, because in other companies it's easy to change code, it's more malleable. So that's another thing to think about. Okay, so what's the point here? I have this problem. I have to teach C++ to a lot of people. How do I know what to prioritize and to avoid? How do I create a style guide? What's the input? And one of the things that we're doing with the book is trying, again, to be kind of objective with the analysis, but also categorizing these features by safety. And what we mean by safety is quite interesting, because every feature is safe if you know how to use it, but there are differences between closing angle brackets and auto. So yeah, every C++ feature is indeed safe when used correctly, but what is the likelihood that it's going to be used correctly and by whom? Does the feature have any attractive nuisance? So this is a term that Lakos uses a lot. I like it. And basically it's the idea that this feature leads you to write code which seems natural and organic for the feature, but actually it's not the right way to use it. And it's kind of, it's attractive because you want to write that. It seems correct, but then actually it's not the right way of using it. And there's a lot of these attractive nuisances in C++. What are the advantages of using a feature compared to its risks? Maybe it's a fantastic feature, but it's really hard to get right. Is it worth it? Or is it worth teaching this feature to a new hire? What about an experienced hire? This might differ. Maybe if you don't want to teach something like, I don't know, inline namespaces to a new hire, but somebody that's going to work on the main libraries of your company might need to know about inline namespaces. So in the book, the definition that we use for safety is this one. The degree of safety of a given feature is the relative likelihood that widespread use of that feature will have positive impact and no adverse effect on a large software company's code base. It is not an exact science, of course. It's a very vague definition, and it's the best we could do because it's really hard to find objective measurements for this. However, we feel like that by relying on teaching and user experience, not just mine and the other authors, but also all the people from the ISO committee we've interviewed and talked to, and all the people from other companies that have reviewed our book, we can get pretty close to a categorization which is useful. And this categorization becomes, as I said, a useful metric to decide what to teach or what to focus on. And it's something that I think can help dealing with the diversity problem and with the problem of style guides. So yeah, we have safe features, and safe features are those that had considerable value. They are easy to use and hard to misuse. And in general, ubiquitous adoption of such features is productive. So go out in the world, talk to people and say, use this feature, it's good. Then we have conditional safe features. These still add considerable value. They are still great features. They can actually solve problems in a very elegant and nice way, but they are prone to misuse, which means we want people to know about these features because they add value, but they need training. They need to know what can go wrong. They need to play around with them. They need exercises. They need some way of experiencing it firsthand. This is how I use the feature, and this is what can go wrong before they actually jump into a real project and use it. And then we have unsafe features. Again, unsafe doesn't mean that this feature is never going to be useful. It means that this feature is going to provide value only in the hands of an expert. And by expert, I mean somebody who is really experienced with this feature. And it is prone to misuse. So you really wouldn't want to teach these as part of the General 11 and 14 course. And probably you don't want to teach these to your friend over a coffee break. You probably want to sit down, have some discussion about it, have some training, and see all the varied niche use cases and the pitfalls that can happen. And there are a few of these in C++, and they can be really useful in some cases, but I wouldn't recommend them in the general case. Okay, so just to get the point across, my prime example of a safe feature is the override keyword. This is literally one of the best things that has ever been added to C++. Why? It's a simple keyword. You can place it on any function that you think should override something in the base class, and the compiler will, kind of like certify that expectation. If the function is overriding, everything is good. If the function is not actually overriding, then it will give you a compile time error. So this prevents bugs, because if your expectation is wrong, the compiler will tell you that it's wrong. Or if somebody comes and changes the signature in the base class, the code will stop compiling rather than suddenly change your runtime behavior. It's a fantastic feature for safety. It makes code self-explanatory. It's not just useful for the compiler, but I'm a human, I'm gonna read your code, and now I see override, and I know this thing overrides. So it produces documentation which cannot be wrong. There are no real technical downsides. It's like perfect feature. However, even this feature has a pitfall. And this is more of a human pitfall. It's not something related to the technical side of this feature. Imagine you are in a big company and you get taught about override from the very beginning. And you start using it, and everybody uses override over and over again. Every time you write a virtual function, you write override. Except one time you forget. Now, everybody is going to assume that whenever you see override, the function is overriding. And whenever you don't see override, the function is not overriding. So forgetting to put override might lead to somebody believing that the function is not virtual incorrectly and acting on that expectation and potentially introducing a defect. Now, what we call this pitfall over-reliance without enforcement. And fortunately, there is a fix for this, enforcement. So we have static analysis tools. Modern compilers have flags that tell you when you should use override. But it's still a pitfall, right? You need to be able to know that your tool chain will tell you, hey, you have to put override here because it's actually overriding. Otherwise, people might start relying on the presence of override, and if it's not enforced, then they might get wrong expectations. So it's a very minor pitfall, human pitfall, but it's still there. Conditionally safe feature, range-based for loops. They are often great, very nice and elegant way of expressing the idea. I have a range and I want to do something with every element inside the range. I don't need to care about iterators, indices, very simple. However, sometimes they are not as great as they seem. And on this slide, you see some code. This is some code that I wrote a while ago for one of my side projects. It's a game called Open Hexagon. I'm going to have a shameless plug at the end for it. But the idea is like I wanted people to be able to rebind their keys if they don't like the default ones. And I had this array of keyboard trigger getters with some bind IDs that correspond to the in-game actions. And when I call any of these getters, I will get back a trigger getter object. And this trigger getter will expose a getCombos member function that will get me back a vector of combo. And combo is basically a combination of keys. So for example, if you want to jump, you can say that a combo is Control plus Alt or something like that if you are weird. Now, I wrote this code and I basically invoke the getter, get the combos, and then I iterate by taking each combo by reference. And I don't remember what I was doing here. I was checking them or modifying them, and that was pretty much it. So I'm going to ask you, if you look at this code, is there anything that you think is problematic? So somebody said lifetime. Can you elaborate?
Well, get combos is a temporary, and you're taking a non-mutable you're taking a mutable reference, so you're expecting some side effects on the object C, but you have a temporary, right?
Okay, I see what you're saying. You're saying I'm modifying something that's been returned from a temporary, so what's the point of doing that? Potentially this might be an issue, but it might be reasonable to do some mutation on the return of get combos as a local mutation and then pass them on to something else. So I see what you're trying to say. I don't remember what this code was doing, but what I was doing in here was sensible, even if I had a reference here. So somebody's talking about returning a copy doesn't return a reference. Okay. So does anybody think that this code is undefined behavior?
It really depends on what keyword trigger getters indexed on bind ID returns. The for loop will take care of whatever's storing whatever's returned from get combos. But what is get combos passed to that? Like the keyboard trigger getters, if that's a temporary, you got that. There was all that that paper about the for loop and lifetime where you have temporaries constructed to get to the final state there, and if that's a temporary that is passed to get combos, it could be dangling.
Okay. So this code is a bit scary. And the reason why it's scary to people is because there is some temporary business going on here. Maybe this is returning a temporary, get combos is returning by value. And some people have often said in conferences or on Twitter or whatever that range-based for loops don't work well with temporaries and you can get into lifetime issues. However, your fears are justified, but this code is completely fine. Like, it doesn't really matter if this thing returns by value or by reference. It doesn't really matter if get combos returns by value here. In fact, like, there are absolutely no lifetime issues with this code. Works fine, and it worked fine for a long time. Until I added an optimization. So what I did was I completely forgot about this thing over here. I didn't care about it. But I was looking at code and was like, hey, this thing is returning by value, and inside this get combos, I'm recomputing these combos from the config file every time I call it. That's kind of wasteful. I didn't profile or anything. I just saw something and I say, yeah, I'll optimize it, right? That's what everybody does. And what I did to optimize it was I cached those combos into a data member of trigger getter. And rather than recomputing them every time, on the first call to get combos, I would compute them and cache them into the vector. And then when I return from get combos, I would actually return a const reference to the vector. So now, after I implemented this optimization, something broke in my replay system, which was completely irrelevant. Everything compiled, it was fine, no warnings, nothing, but my replay system started breaking in some weird cases. And then I went through address sanitizer, and address sanitizer told me, hey, look, you have undefined behavior in this loop over here. And I was confused because this has been working for months, but a change I made into trigger getter actually made this become undefined behavior. And now you see that issue with the lifetime that you were mentioning. It's very specific and it's very subtle. The fact is that when you have a range-based for loop, the whole expression that you use to iterate on, so the whole range expression, gets bound to a reference internally. You don't see it, but internally what happens is that this range-based for loop gets converted to a normal traditional for loop, and the range is bound to a reference. And if the range is a PR value expression, so if this thing is a PR value expression, which means a pure R value expression, so something that was born as a temporary, like a function returning by value. If you return something by value, it's a temporary that was born as such. It's a pure R value. Then everything is fine because there's a rule called lifetime extension, which says whenever you bind a PR value expression to a reference, the lifetime of the object that the PR value expression evaluates to will be extended to match the lifetime of the reference. So the lifetime is extended for something that's returned by value. However, once we change the return type to something returned by reference, lifetime extension doesn't work anymore because it's very specific. It's only for PR value expressions. This is not a PR value expression anymore. It's an L value expression, GL value. And I don't get lifetime extension. So on the right before the first iteration of this loop, this reference becomes dangling because this thing returned a temporary. This is now a reference to something that's a data member of a temporary, but the temporary was destroyed. It was not extended. So anything I do with C is going to be completely undefined behavior. So what am I trying to say here? Range-based for loop are a great tool. They work well, but there's a lot of complexity and subtlety behind them. And many people had the right intuition. There might be something wrong with lifetimes here. But being precise and knowing when that is wrong and why it is wrong requires a knowledge of weird things. Lifetime extension, PR values, the difference between returning by value and by reference in terms of value categories. Why do I need to know all these things if I'm just going to write a loop, right? And this is why we think this is a conditional safe feature, because most of the use cases are totally fine and they are beneficial. They're going to make your code nicer and better. But there are these pitfalls which come out of the blue, and they can come as a result of changing some part of the code which was not related, like this one over here. And you need some training. You need to know what can go wrong and why. And therefore, when I explain range-based for loops, there is no way I'm not going to explain lifetime extension and why it is the way it is, because people will encounter it. It's something that will happen, and I want people to use range-based for loop, but I also want them to understand when they can go wrong. There was a paper from Nikolai Yosudis, Viktor Zverovic, and some other people. It was called Fix the Range-Based for Loop. And the goal of this paper was basically changing the way the range-based for loop would be expanded to by the compiler to something slightly different, which always extended the lifetime of the range expression to the entire duration of the loop. The solution was quite nice. It had some edge cases which were weird, but definitely much better solution than what we had before. But it was rejected by the ISO committee. And the reason was that they wanted a more general solution that works everywhere, not just for the range-based for loop. Now, this is quite sad. I'm personally of the opinion that perfect is the enemy of good, and this would have solved an issue that has been plaguing beginners and people using range-based for loop for a long time. And the edge cases that were described in the paper were not that big of a deal, to be honest. The situation would have been better. But in general, like, this is what we have in C++, and that's the mindset of the committee, unless it's a, well-defined thing that encompasses the whole language, then they are not gonna patch holes. I don't know how good of idea is that, because this would have been a nice fix, but that's what it is. So this got rejected. Therefore, we are still saying that this is a conditionally safe feature, and we couldn't upgrade it to a safe feature. Okay, any questions so far on anything we've seen or on this example over here? If you want to go a bit more in detail on why this doesn't work, I can also explain that or show you the expansion.
I recall a while ago that people were recommending to use R value references in this case. Is that still a good recommendation?
You're probably thinking of Autorefref, right? Sorry, you're probably thinking of Autorefref here?
Yeah.
Yeah, so that's not an R by reference. That would be a forwarding reference.
Right.
The recommendation, I think, so I remember, I think it was an article by Arthur, if I'm not mistaken, and it was saying that you should use Autorefref there because it always works. But I completely disagree with that, because it's like saying you should use void star every time you use a pointer because void star always works. In my opinion, if you use a tool, like for me, the definition of simplicity in code is using the tool that's most limited and gets the job done. So when you can get a pointer to an int, use an int star, don't use a void star. If you don't need the null state, use an int ref, don't use an int star, right? Use the most limited tool, because that reduces the surface area of possible things you have to think about, reduces the moving parts. So if now you're using Autorefref for an array of integers instead of int, you are making your code more complicated for no particular reason. Yeah, it will work. It will work with int, with float, with everything, but it's a tool that's too flexible. It's like using, a jackhammer to put a picture on the wall. So it will work, but it's a bit extreme. So my advice is, like, don't be lazy. If you don't know what should be there, think about it, because using Autorefref will probably work, but it means that you don't really understand your own code. There are also some places where Autorefref is the thing that needs to be used. Some places, for example, where you have inside of a template, this range expression returns something that you don't know what the value category is, and then you want to forward it inside the loop or something like that. Then at that point, you want to use Autorefref. And I think that limiting the usages of those more flexible features for the places where they really need to be used is a better advice rather than blindly using them everywhere. So I think that's what you were referring to. Right.
Yeah, but then, people are refactoring their code all the time, and they might bump into the same issue you bumped into.
Yeah, but my issue is completely unrelated to this bit over here. Like, what's before the colon does not affect the lifetime at all. It's what's after the colon that's the problem. So this could be autoref, it doesn't matter. The lifetime of the range is controlled specifically by what's after the colon and the value category of this expression over here.
Okay, makes sense. Thank you.
Okay. And finally, example of an unsafe feature, decal type auto. And decal type auto is one of the features that has some very important use cases. For example, if you're writing any sort of super generic library that takes some higher order function, like in this case over here, I want to take some generic function object f and then log something and then invoke it. Then by using decal type auto as my return type, I will ensure that whatever f returns, whether it's a reference, a value, a const reference, a volatile value, is going to be preserved when I invoke the function after forwarding it. If you were to use auto here, then it would always make a copy. If you were to use autoref, it would always return a reference. But by using decal type auto, this is super flexible and it does exactly what f needs. It returns exactly what f returns. However, people see this and they think about it as a more powerful auto. So it gets misused. It gets used in some places where auto would have sufficed or where Autorefref would have sufficed. And again, I'm of the opinion that you should use decal type auto only when it's strictly required. And I think that the use cases for that are very far and in between. So what I did, I used to teach decal type auto right after auto and decal type. My train of thought was really simple. It's just like, okay, I'm teaching auto. People understand auto. then I'm going to teach decl type, which is an extension of auto. Auto always uses the initialization expression as the candidate from which to deduce the type. Decl type allows you to specify any arbitrary expression. And then I'm like, okay, I taught auto, I taught decl type, it's time to teach decl type auto. My idea was I'm going to provide, this nice progression, but the actual result was different. People started overusing decl type auto. And after talking to some students, the comments were, if decl type auto does what auto can and more, why not always use decl type auto? It seems just better, right? Or maybe sometimes I don't know whether I should use auto and Autoref. I'm not really sure. So why think? I'm just going to say decl type auto and the compiler is going to do the thinking for me. And again, this is sort of the thing I was talking about 1 minute ago. Like, you need to understand your code, and you need to understand that if you use a tool that's too flexible, you're going to make it harder for the people to understand your code. If you restrict what you can do with a certain tool, the surface area is smaller, less moving parts, code is simpler. So this is not what I wanted. So now I still teach it, but I'm very rigorous in my wording, and I make it very obvious that this thing should be used very sparingly. And I want people to know about it, but I also want them to not jump on it unless they know it's the right answer. And in general, to know when decl type auto is the right answer, you need to have a very solid grasp on type inference and value categories. You need to understand what is an X value, what is a PR value, what is a GL value. You need to be familiar and experienced with both decl type and auto. It's a combination of both. And then, since this thing only really is useful in the context of metaprogramming or heavily templated code, you need to have some metaprogramming experience. For example, have used Spinner before. Another cool thing is that I really couldn't find any valid use case for decl type auto in variable position. Like, most of the use cases I found are all in the return type position, like used as a placeholder for the return type. I put a star here because I recently found maybe a possible one, but I'm not 100% sure. It's kind of like, yeah, this helps solve the issue, but then when I look at it, I'm just like, maybe the whole design is crap, right? So there might be some places where this could be used as a nice patch or glue, but I'm begging you, if you have a use case, a killer use case for decl type auto in variable position, where it's like, I'm looking at it and I'm like, yeah, I couldn't write this code in any other way, decl type auto is the best tool here, please share with me. Because I've been looking for that. I've asked a lot of people, and nobody was able to come up with an example where decl type auto in variable position is the simpler way of expressing a certain semantic or piece of code. So if you have that, I'd be delighted to discuss it. So yeah, and even when you use it as a return type, there's still an alternative. The alternative is using a train return type. I could rewrite this with auto, log and call, f arrow, decl type stood forward f of f. And at that point, there are some differences. For example, the decl type auto version is not SFINAE friendly. You won't be able to detect whether this expression is valid or not at compile time. If you're trying to SFINAE on this, it will be too late. You will get an error as part of the instantiation of the template. If you instead use a train return type, like with the arrow, decl type, stood forward f and whatever, that expression will be visible at the time of substitution, therefore SFINAE might take place. So they look the same, but they're not the same. They are actually quite different for the purpose of metaprogramming. Yeah, point being, this is far from trivial. It requires knowledge and it requires experience. So this is why we call it unsafe. Not because it's a bad feature, not because it's useless, but because the cost-benefit ratio and the amount of training involved doesn't justify, widespread adoption in a company or in a team. These are the statistics about safety, and fortunately, most things are either safe or conditionally safe. So in 11, we have 18 safe feature, 21 conditionally safe, and 7 unsafe. In 14, 5, 3, and 2. So fortunately, there are only a few features that we feel like should be used very sparingly. The rest of the features are good, which means they are the cost-benefit ratio for most of the things that were added in modern C++ 11 and 14 is positive, which is nice. Some more examples of safe features are attributes, null pointer, static assertion, digit separators, nice quality of life improvements. Conditionally safe, auto, constexpr, R-value references, and all the move semantic business. And unsafe, carries dependency, final, inline namespace, things that are a bit more, should be used more sparingly. Final, for example, is one of those that people often say, why is it unsafe? And this is from experience at scale. Like so we have to be clear here. There are some companies that, as I mentioned before, like Google, where for them it's super easy to do a full-scale refactoring over the entire company or over a PR that covers multiple teams and stuff like that. For companies like Bloomberg and I think the rest of the world, that's a bit harder. So imagine you are, let's say, somebody new to C++, and you come from Java, you know about Final in Java, then you learn about Final in C++11, and now you start using Final on any class that's not polymorphic. Like you write a simple class, shouldn't derive from it, so you use Final. Or you are part of a polymorphic hierarchy, and you think you are at the leaves of the tree, and you use Final. You do this, and then somebody in some other team actually has a use case for which they want to inherit from your class. You know, even in C++, even if your class is not polymorphic, even if your class doesn't have virtual member function, inheritance might still be a good idea in order to avoid code repetition and basically, you know, augment the interface of your type with some extra member functions or delete some of them. It can be useful to actually derive from a non-polymorphic class and tweak the interface or something like that. Or even add data members if you know that you're not gonna have any object slicing. And now this thing is marked as final, and I have to go to the person in the other team and tell them, look, I would like to inherit from this. I have a good use case. Why did you mark it final? And they're like, okay, I didn't know. And then I have to send a PR. It needs to go through CI. It needs to be deployed to the packaging system. And then I can finally use it when it's available in production. So at scale, we feel that overuse of final can actually harm reusability of code. And especially at large companies, reusability of code is key to get stuff done quickly and without friction. Again, this depends on the company. Google, if you have this problem, they just send a PR and it's done. For us, it takes quite a while to get a fix like this rolled out, depending on the severity of the depth of this chain of changes. Yeah, there are other points about final in the book. I don't recall all of them, but the point here that's for us, the cost-benefit ratio and the cost of training people on final is not worth the hassle. Like, the benefits are so little and widespread, like it's not gonna make your code any better. And in general, if you're using it as a way of optimizing your code to relying on devirtualization, then maybe you shouldn't have used virtual in the first place. Like if the performance of your program has a bottleneck due to virtual dispatch, then that's telling you something. It's not telling you to use final. It's telling you, hey, maybe you should do some data-oriented programming or think about the memory layout of your types. So that's why we think it's unsafe. And again, it doesn't mean it's a bad feature. It just means that in general is probably the last thing I would want to teach somebody, and I don't see that much of a benefit in the first place. Does that satisfy anybody, or is anybody a huge fan of final and wanna say something? Okay, we can discuss at the end if you have more opinions on this stuff. Yeah, so I don't want to repeat myself. I'm gonna go quickly through this, but my strategy nowadays is teach safe features early and quickly. Trust your students. They are not likely gonna screw up. They are usually quality of life improvements, are to misuse, so we don't need to worry about this too much. Conditional safe features, teach them by building on top of the safe knowledge. And they require time and examples. You have to show how they can backfire. Example, range-based for loop. I'm not gonna teach the range-based for loop without showing people the temporary issue. And in general, for these features, I want to have exercises. I want the students to actually play around with them and, figure out, hey, maybe I should use it here, maybe I shouldn't use it here. Like, make them question whether to use it or not. And for unsafe features, I would leave this to self-contained CE courses, continuous education courses. So I'm gonna have a 1-hour course on inline namespaces, and I'm gonna have this nice course on library, API, and API versioning with inline namespaces. It's something that requires a little bit more thought and a little bit more, guided understanding of the feature. So I wouldn't want to teach this as a general purpose course, but it's totally fine to teach them for their own specific niche. Okay. If there are no questions, we are going to take a look at one example on extended friends. Any questions so far? we don't say compile expire, we say godbolt. That's how you don't make the mistake. Okay, cool. So I'm going to talk a little bit about extended friend declarations, and this is a bit that I extracted from the book. There's way more on this on the book. This is just one of the use cases. So if you don't know, what happened with friendship in 11 is that we got a new feature that is called extended friend declarations, and this is an extension of the previous syntax that actually is way more flexible. Prior to 11, whenever you wanted to befriend a type from another type, you needed to specify something called an elaborator type specifier as part of the syntax. And this is a syntactical element that has this form. You say either class, struct, or union, and then you provide an identifier. And this is what is called an elaborator type specifier. So for example, I could have a struct s, and then I could have a struct example, and I could say friend class s over here. And that would be fine because it follows this syntax, class, identifier, class s. But I can also say friend class non-existent. And even though I never declared a type called non-existent before, for some reason this compiles. And the issue here is that before 11, if you use the syntax, you're actually declaring a type. So not only you are saying I want to befriend something, but you're saying I want to befriend something that I'm also declaring at the same time. So you might create a type out of the blue, like non-existent, and make it your friend, which is pretty useless. But that was possible in C++3. And this restriction on the syntax limited friendship between types only to classes, structs, or unions. So if you have any other sort of type, you cannot befriend it in C++3. And by that, I mean if you have a type alias or a template parameter or a decal type expression, all these things are valid types, but they cannot be used with the friend syntax. So for example, if I have a using window manager type alias to a Unix window manager, or if I have a template type name T, then either friend class window manager or friend class T would result in a compile time error in C++3. I cannot befriend these things, even though conceptually I should be able to. So in another thing that I wanna forget is that the fact that friends are declarations in C++3 can be very surprising sometimes. So for example, you might have the use case where you have a struct s in some namespace, in this case the global namespace, and then from your namespace ns, you might have a class x3, and inside your class you say friend struct s. So now anybody would expect this thing to actually befriend the global s, but it doesn't. This actually declares a brand new type s inside the ns namespace, and it doesn't refer to the colon s. So it's annoying. I think you can make this work if you specify the scope resolution operator, or if you are clever in the way you define this. But again, the simple thing doesn't do the thing you expect in C++3 because you are declaring a new struct over here. Okay, 11 tries to fix all of this stuff by adding this new syntax where you simply say friend and a type without specifying class, struct, or anything. So this is not a declaration anymore. It does not declare anything, but it expects you to give it some sort of type name, which is already available in the scope, something that can be looked up via name lookup. So for example, I can say friend T, where T is the template parameter. That will work. I can say friend S, and it's not going to declare a new S. It's going to look for the first S via name lookup. It's going to find this one, and it's going to be fine. It's going to refer to the global S. I can also befriend a type alias. So S alias over here will also work. I can also do something like friend decal type of 0, which is the same as friend int. Not very useful, but you can do it. And if you try to say friend C, where C is something that you just came up with, it doesn't exist anywhere else, it will give you an error. We don't like C. We don't want to be a friend of C, so that will be a compile time error. However, even though it seems like this feature solves problems, we mark it as unsafe in the book. Why? There's two main reasons. So the first one is that if our book actually were to cover C++3 features as well, friends in general would be unsafe. And again, the reason is kind of like final. It's not inherently bad. There are good use cases for friendship, but it's not something you want to tell people, especially new hires, because they're going to go and use friends everywhere when they have an issue with encapsulation or their design is suboptimal. So friend has a very high cost, has a very, very negative cost to benefit ratio. in the terms that it can actually make your code really poorly coupled, can make things hard to test, and it's not something I would recommend. There are only a few places where I think friendship is reasonable. The other thing is like this flexibility actually makes the problem worse, because before, if you see this slide over here, you are kind of limited to befriending things in your namespace, right? You cannot befriend things in other namespaces easily. While with the new syntax, you can befriend whatever you want, right? You can befriend something that the user gives you, something in another namespace. So this actually promotes long-distance friendship. And what we mean by this is friendship between things that are physically away from each other in terms of component or physical components. So if I have, my header and CPP file here, my header and CPP file here, they are completely independent, and I befriend them, then they become physically coupled, because even though they are logically not coupled, now they need to refer to each other if they are friends. And the idea is that if you have a type X that befriends a type Y, which lives in a separate physical component, which could be, another module in your library, another library, even worse, then you put yourself in a position where X and Y cannot never be tested independently anymore. Because if you test X, you are depending on Y and vice versa. And this is pretty bad for any sort of reusable large-scale code system or anything like that. Even worse, if you have a cycle of dependencies like this one, and you use friendship, you might inadvertently create a physical design cycle where basically you have a loop of components that refer to each other. And again, testing one independently cannot be done because you have to test all of them together as they are coupled together. It's not good for testability, it's not good for compilation times, and it just makes your design a bit of a mess. However, this seems like it's a terrible feature, but there are good use cases for extended friend declarations. And an example, which seems pretty weird, is avoiding typos. It's a very small thing, but it's actually beneficial. So one of the cases where I think that friendship is possibly a good idea is where you have, for example, a very big class like a list and then a list iterator. The iterator is conceptually part of the same thing, as part of the list, is a separate class, but it doesn't make sense without the main class, and it might need access to the private members. So befriending iterator from the container class is something that is usually reasonable. C++3, if I make a type, when if I say something like let's iterator over here, then this will compile and it will simply declare a new type called let's iterator. Well, I obviously meant to say list. I mean, it's not really going to probably cause any runtime defect. Eventually it's going to be caught in some other place in your code, but it's still going to be a waste of time. Why is the compiler letting me do this? Why do I have to recompile and fix it and whatever? In 11, if you make a typo by using the new syntax like friend, let's iterator, this will immediately fail to compile and tell you, look, there is no such type. You have a typo, you should fix it. So even for small things like this one, using the newer syntax can be beneficial because it kind of guarantees that the type you are spelling out exists, which seems like a given, but typos happen. There are other interesting use cases that we cover in the book. There are customization points with type aliases, the passkey idiom, which is more selective friendship. But for the purpose of this talk, I'm going to show some CRTP stuff. There is a question, do we need struct on the right side? Like here, you mean? Yeah, no, you don't need struct there because we are trying to use the new syntax, the C++11 syntax, which doesn't use anything in between the friend keyword and the identifier. So if you were to use struct, you would fall back to the C++3 syntax that will declare a type and it will compile even though you don't have that one. So the new syntax simply takes the name of a type, and that type has to be existent and needs to be found via name lookup at the point where you declare the friendship. Does that make sense? Yes, templates. If you're trying to befriend a template parameter, you will need the extended friend declaration. So you will need the new syntax over here. Okay, CRTP. If you never heard of CRTP, it's an acronym. It stands for Curiously Recurring Template Pattern. And basically, it's when you have this sort of pattern in your code where you have a base class that takes a type name T in a template, and then you derive from it and you pass the derived class itself as part of the template arguments of the base class. It's kind of weird. So basically you have a class derived that is derived from a public base of derived. And the reason why you want to do this is you can now give knowledge to your base class about who is deriving it. So base knows who derives from it because of T. And this actually turns out to be very useful in practice because it allows you to implement mix-ins, implement compile time polymorphism, and factor out copy-pasted code. So you can imagine, for example, that base might have a function that does some common code shared by a lot of other classes. And then you have a customization point, which is defined in derived class. And base will be able to jump to the customization point at compile time because it knows what T is, it knows what the derived class is. So you can static cast this pointer to a T star and then access the derived class behavior over here. So it can be useful for this kind of things. And for example, if you look at strong type def libraries that allow you to specify strong type defs, usually they use this behavior to allow you to inject operators and things like that into your derived class. A lot of cool stuff you can do with CRTP. But what we're going to focus on now is this idea of factoring out copy-pasted code. The example we have here is basically an instance counter. Let's assume, for example, for testing reasons or for metrics, I want to know how many times an object is constructed and destroyed in its lifetime. A type is constructed and destroyed in its lifetime. So how many instances of a type I have at any point in time. One of the things you could do is you have your class A. It will have this static int scount, which is your declaration. Then I'm going to have a public getter for this scount that tells me what the counter is. And then I'm going to increment it on construction, copy construction, move construction, and decrement it on destruction. And then, of course, since this is not an inline variable and it's a static data member, you would have to provide a definition in the CPP file, and this should probably be initialized to 0. So sorry about that, but imagine it is. But you still have to provide the definition in the CPP file and have this kind of separation between the header and the source. Now, this is fine if you have a single class, but imagine we want to track the instance usage of 5 classes, A, B, C, D, and E. I don't really want to go and copy paste these things 5 times and also define 5 CPP files to provide storage for my static data member. So what I can do is try to refactor this to reduce the repetition. However, we need to basically have a counter per type, and we need to be able to access that counter from the constructors of this type. So how can we do that? We cannot do that with normal inheritance, because if we simply had a base class that has the counter, then it would always be the same counter for each type. So we want to introduce some sort of way of creating a generic counter for a type without having to spell it out explicitly. One way we can do that is by using CRTP. We can have a CRTP base class called instance counter. It takes a type name T, which is going to be the derived class, and then it exposes the static int as count via a protected access specifier so that whoever is deriving from instance counter can actually mutate it on construction and destruction. And you're going to have the public accessor, and as an added benefit, since this is a template, it is going to be inline, so we can provide a definition for this data member, static data member, in the same file, so we don't need to have the CPP file and all that stuff. It's going to be inline storage. What else? So the reason why this counter is going to be unique per type is, of course, because when we instantiate this template using the derived type, is going to be a different one, and it's going to generate a brand new static data member for each instantiation, which is going to allow us to count them. Okay, great. Now I'm going to use it. I'm going to have A derived from it. I'm going to have B derived from it. I'm going to increment the counter, and everything is going to be fine, right? Or is there any issue with this usage of instance counter? Everybody happy with this code? It compiles.
The second one ought to be instance counter B to begin with.
Yeah, exactly. So this compiles. It will do the wrong thing at runtime because we made a typo. We said instance counter of A. And like, you would expect this to not compile, but it does. And this actually compiles as well. It's going to change the counter of the previous one. And the problem here is that we don't really have any requirement that B and whatever we pass with instance counter match. We are saying this can be any arbitrary T, S count is going to be protected, so it doesn't matter. As long as we derive from it, we can access it. And, since we were trying to avoid, major copy pasting, we ended up with a copy paste mistake, which is quite ironic, but this can happen. So how can we prevent this? And it seems that we find friendship in the most unexpected of places, because extended friend declarations can actually prevent this mistake. Another issue that might happen is that you might have a class further down the hierarchy that derives from A, for example, and it still has access to S count because it's protected, and it could mess with it. Like, why would you do this? Hiram's law. If something is possible, somebody is gonna do it, which is basically very true in software development. So we like to prevent these mistakes. We want to prevent hijacking of the counter, and it turns out that extended friend declaration actually solve both issues in a surprising way. So if you redefine your instance counter like this, you turn S count from protected to private, and you befriend your template parameter T, which is only possible with the 11 syntax. Now you are implicitly adding this requirement that T is the only one that can touch the counter. And since this is a CRTP base, it means that T must match with the base and no one else can touch the counter. So we change the idea, it's not protected anymore, it's private, and we have a single thing that can access it, which is going to be our derived class. And once we do this, if you make this mistake over here, you won't be able to access the counter. The compiler will tell you, hey, you're doing something wrong. If you're trying to hijack the counter from a class further down the hierarchy, again, the compiler will tell you that you are not able to do it. So this is an example where I think a very unusual combination of things, CRTP and friendship, work well together. And I actually recommend this pattern whenever you use CRTP, because you are adding extra compile time safety to your program, catching defects at compile time, and ensuring that the visibility of your commonly shared things is only available to the derived type and not to anybody else. And it's quite interesting. It was something that I didn't know before going into my 3 years research of 11 and 14, and it's been an interesting find. I see a hand raised up. Yeah.
But then you can't have any privates inside instance counter, right?
You can. You would have to use the passkey idiom if you want to have that selective friendship. And the idea is, if you wanna be more fine-grained, if you wanna do something like, I want only the counter to be visible from only T, you can achieve that with the passkey idiom. So there are ways you can have more selective and fine-grained friendship. It's a bit more extra code. You always have to be pragmatic, maybe it will be worth it, maybe not, but it is possible.
Right.
I think in general this is better than before. That's what I'm trying to say, because before literally anybody can access this counter. You could have privates, yes, but for this particular case we didn't really need them. Maybe with another use case it would be better to not use the friendship. Like, it depends on the context. I want to be completely honest, right? For this particular use case and for many others that we cover in the book, it actually is beneficial to perform this friendship trick. But it's a good observation, absolutely. You can work around with the passkey idiom, but that's a bit of extra boilerplate for sure. There was a question, why doesn't the counter return a reference? We don't want this to be mutable. We want this to be a view-only getter. So like, it returns by value, so you cannot actually mutate the count. Okay, so yeah, this friend declaration seems limited at first. They can also promote bad design, like physical coupling, long-distance friendships, but they have nice properties. They can avoid typos and mistakes, and they have some good synergy with CRTP in particular use cases. However, again, niche feature, something that you don't want to teach somebody that is just learning C++ or somebody who's having his first approach or her first approach with modern C++. So unsafe is something that where the cost-benefit ratio is quite unappealing. So we need training, we need experience. The use cases are very rare and niche. So that's why we call it unsafe and why we want to, discourage it being taught more widely. But again, has some nice properties, some good use cases, And I think that's the kind of analysis that we're doing in this book. We're trying to see all the possible things that can go well, all the possible things that can go wrong, how generally beneficial something would be for your average company or a large-scale company, and then this is what comes as an input for our categorization. But we're not saying that any feature is good or bad. We're just trying to give you some guidance on where to start and what to teach. So that's pretty much it. In general, what I've learned is that even nowadays, 11 and 14 are kind of still about open research area. You know, it's always easy to look at the features in isolation and play with toy programs and get some ideas of how these features can help. But when you start thinking about, hey, I have 4,000 employees and I'm going to teach them these features, then it gets really tricky. And the human cost of a feature is not easy to quantify. Override was a good example. If you start relying on it, then you can make the human mistake of over-relying on it. Or if you teach something too early or in a poor way, then maybe over the course of a year, that thing is going to prevent you from refactoring your code, or is going to have a lot of technical debt that you could have avoided with proper teaching. In general, we found that categorizing these features by safety helps with devising learning paths. You know, if I'm responsible for creating a course or for creating a style guide or some set of guidelines for a company or a team or whatever, then I find it useful to at least think twice if I'm going to include that unsafe feature. And I find it useful to remind myself that conditionally safe features need a little bit more exposition and exercises. So I find that useful as a you know, a guiding principle. And in general, you know, all features, all of them have good use cases and nasty pitfalls. So again, gonna be kind of like repeat a common way of saying things, but knowledge is power, and I think that's always true. Or knowledge has power? I think knowledge is power. I think that's better, but yeah. So thank you. This is the book. It's gonna be out on the 23rd of December 2021. It is available now for pre-order. If you go on this website over here, you will find various you know, resellers. The publisher is Pearson. You can buy them directly from them or on Amazon, on other places. You should be able to find it anywhere, to be honest. If you want to follow me on Twitter for updates, I'll let you know when it's actually out. But I think this 23rd of December is the date. And this is a list of people, which is not complete, of people that have contributed. So these are the main authors, but there's also been Andrea Alexandrescu, which wrote sporadic templates for us and reviewed, and a foreword. So people from the Standard Committee, you might recognize Pablo Harpen or Nina. They've been in the Standard Committee for decades. And then some people like Sean Parent and some other people from Bloomberg that have had a lot of experience with writing low-level libraries and have been in the company for decades as well. So I think there is a lot of varied experience and point of view, a lot of diversity, which is good, because if you want to teach diverse set of people, you need diverse set of opinions and experiences to get the best possible result and you know, help people get to the right conclusions. So thank you, everybody. That's pretty much it. Shameless plug for my game. If you like games and you like hard games, frustrating ones, I released this open source 17 game on Steam and itch.io. You can play around with it. It's basically a spiritual successor to Super Hexagon, if you played it before. I have the blessing of the original author, so it's not a shameless clone. But yeah, you can check it out if you like games, or if you want to have some open source game to play around with and you know, contribute or whatever. And this finally is the list, the table of contents of the book. So if you want to ask anything like, why is this feature safe, or why do you think this feature is not safe, and so on, this could spark some discussion. So I'm happy to take any questions and discuss, argue, debate, and yeah, feel free to ask me anything.
Everybody, let's give a virtual thanks before we have questions to Vittorio, because that was a fantastic talk.
Thank you. I appreciate that.
Let me see your clapping hand icons. I have one question. I think I put in the chat, I love this idea of categorizing features according to safety and leaving the black and white world behind and learning to kind of love this gray world. You're focusing on education. have you seen anyone try, or have you tried to integrate these ideas into enforcement as well?
So, in particular, I think this relates to the point I was making on style guides. Maybe I've used the term style guide a bit in the wrong way. For us, like when we say style guide at Bloomberg, we talk about coding guidelines. So it's not just about style, but also what people are encouraged to use and not used. And one of the things we're doing with the book is it has gone through the CTO office and everybody, and it's been reviewed. And we are trying to modernize and review our coding guidelines depending on this particular categorization. So for example, one thing we want to do, because the coding guidelines are quite old, they're mostly for C++03. So when we're going to update them for 11 and 14 and 17, this is going to be a good place to get some guidance. Like, we definitely don't want to say something like you should use final or any non-polymorphic class. We don't want to say you should use no except whatever you don't think an exception is going to be thrown, because there are good reasons to not do that we explain in the book. For example, it's quite common that somebody just writes a small function and it's never going to throw, and they put no except on it. Is it a good idea? Is it a bad idea? Generally, it's a good idea, but there are some cases where it might actually generate more code and produce more overhead. It's kind of weird, but it's because of the requirement for terminate. I'm going to go on a tangent here, but it doesn't matter. So the thing is, like, when you have a function which is marked as no except, the standard requires that whenever an exception is thrown from the body of this function, terminate will be called. So it's not undefined behavior, it's well-defined behavior, which means that if the compiler cannot prove statically that the body of your function is not going to throw, and maybe there's something which is not visible, something that's not inlineable, or the compiler just isn't clever enough, then it is possible that the compiler will insert extra operations. It will say, this is the body of your function, I'm going to insert a catch, because if I catch an exception, I have to call terminate. So marking a function as no except might be more expensive than not doing it, because the compiler will have to check if you have thrown an exception because it needs to call terminate. It's very counterintuitive, but that's an example of something that we've seen with some compilers, some architectures, and one of the things that might be a guiding principle. Like, it would be totally reasonable for me to just learn about no except and be like, okay, this should be used whenever I don't throw an exception. So I could go to my company and go to my coding guidelines and say, whenever you write a function and you're sure that it doesn't throw an exception, then mark it as no except. Like, it sounds reasonable, but in practice, it might actually have the opposite effect, which is weird, and it depends on the compiler. It's not all compilers that do this, but this is one of the things that I think would be helpful for guidance in actual programming. I don't know if I answered your question. I hope I did.
Yeah, I think that's it. I will be fascinated to see. Hopefully you can give a future talk on how you've integrated them into these coding standards and the processes surrounding the coding standards, because I think that would also be really interesting.
Cool.
Anybody have any other questions?
Check the chat. There's been some discussion in the chat.
Indeed.
There was a question before that I didn't answer because it was a bit unrelated, but I want to go back to it. Yeah, somebody asked, do you use OpenMP with C++ at Bloomberg? Answer is, I don't know. Bloomberg is huge, and teams do whatever they want. So probably, I would be surprised if we didn't. Let's put it this way. There's going to be somebody inside the company that needs performance and likes some OpenMP and uses it. So it's very varied environment. Like, each team is pretty free to choose whatever they want to use. Some people use Scala, Haskell. Some people use C++03. Some people use C++17, and you see different coding styles. It's good in one way and bad in the other, because it is not as consistent as in other places, but also it gives you the extra freedom to get to your goal the way you want to. So I'm sure there is somebody using OpenMP, yes. There was another question about lambdas. Do you consider lambdas as unsafe? No, lambdas are considered conditionally safe, I hope. Where are they? Yes, lambdas. And, in general, they're like nice. However, there are some considerations we make. For example, a lot of captures could lead to bigger size of lambdas, and sometimes compilers have trouble optimizing that out. Even GCC, the latest versions, can have a bit of trouble inlining those things. Other consideration is if you capture everything by reference and your lambda outlives the scope in which it was created, then you need to be careful to make sure the lifetime of the things you captured is still valid. There are things like here and there. There's some annoyances as well. For example, minor things, there's no way to mark a lambda as no discard, for example. You cannot put attributes on a lambda in the same way you could do with a function. That's also pretty annoying sometimes. So in general, we put it here because lambdas are a great tool. We want people to use them, but we want them to be aware of what could go wrong. Similar to range-based for loops, same idea there. Let's see. I didn't understand the loop on slide 34. Okay, let's go back in time. So if you want to do this without range-based for loop, what would you do? So what I could do is, let me actually share an editor or something. Let me see if I can do this. Okay, do you see my editor? Yeah. So if I had this code, which I'm gonna copy paste from the slide source, just bear with me a second so I don't have to type it again. Like, what you could do is, if I didn't have range-based for loop, I would probably do something like this. I would say Autorefref or something like that, combos, and then I would have my for auto it combos begin plus it, and then whatever. So now you get the same issue, right? You still have the same problem. If get combos returns a reference, then so a reference to something that is tied to the lifetime of this temporary, then this would be a dangling reference. The difference is that here I see it, like I can see the reference. And if I know that I'm taking a reference to something, like with anything else in C++, I know that the lifetime of the reference has to be, has to outlive the actual thing. So maybe in this case, I would have still hit the bug, but at least I would know where to find it. The problem with the range-based for loop is that it hides this detail. It's under the hood, and it's not obvious that this thing is going to be bound to a reference. You need to know what this expands to. So that's the problem I have with it. Because in the normal case, you see the reference, it's there, right? And maybe I would have written auto combos and avoid the problem in the first place, right? But here it's completely hidden, it's not in your control, and you need to know, like you have to be aware of what this expands to in order to figure out this problem. And this is why you need the training for it. Does that answer your question? Cool. Was a question on lambdas conditionally safe due to some lifetime issues with temporaries as well? Possibly, if you have a lambda that is capturing something and then you return the lambda by value, you create a copy or move of the lambda, you have to be careful about that thing that you captured still being alive. That's one possible thing. Lambdas itself being temporaries can be problematic as any other object. There's nothing special about them. They're just like object instances of a compiler generated closure type. So I don't think it's specific to lambdas. It's mostly like the captures that can have lifetime issues. What's the name of the game? The name of the game you made? I'm just gonna link it to you in the chat so you can take a look and see if it's your thing. Did I miss any other questions? Oh, there was this comment by Eric. It would be nice if the C++ standard had a mode that would enforce all the no safety checks at the cost of breaking compatibility with legacy code that is unsafe. So I was like, if you're thinking about a language feature, I actually wrote a proposal for something that was called epochs, and it was inspired by Rust editions. It didn't fly. It could be fixed. Like it's like people wanted it, but there are some technical issues with templates. Like if you have a template in one epoch, what does it do in the other epoch? It could all be fixed. I just didn't want to deal with the whole standard committee process because it's very grueling and I had other priorities at the time. But yeah, if you're thinking about something like use strict of JavaScript in C++, it is possible. Like it will need a little bit of work and people behind it and proposing it and going through the committee. Some people are opposed to it on a design level, especially people like Bjarne Strustrup, which has a bit of influence in the committee. So you will need to be able to convince people otherwise. It's not impossible. A lot of people disagree with Bjarne anyway. So it is possible. It needs time and effort, and you need to lose a bit of hair by moving this proposal forward. I just wasn't in the mood for it at that time, but it's something I might pick up later. The best possible thing you can do today is static analysis. For example, if you use Clang Tidy, if you use other static analysis tools, you can set flags that tell you, I don't want this to happen, or I don't want this feature to be used. Like you can do those things. And if you have a nice build system where your static analysis is run every single time, you can sort of enforce the things that you want for yourself and kind of make your coding guidelines a little bit more automated. It takes time. You might need to implement your own Clang checks. You can do that. It's open source. It's quite easy actually to do it. There's a lot of, I think there was a talk in CPPCon maybe 2 years ago on how to implement a Clang tidy check, and it's quite straightforward. So something you might want to look into. But yeah, no easy answer. There is C++ is inherently complicated language, and there is no way of reducing the surface area. Every standard will increase the surface area. There's no way around that. Very random to use tab 9 in VS Code. I've been experimenting with it for like past week, so it's something new. Sometimes I like it, sometimes I hate it. Sometimes it completes in the way I want, sometimes it doesn't. I haven't made up my mind yet. I'm currently using it, but it's literally like since 1 week. You might want to ask me again in 1 month, and we'll see.
Okay, let's thank Vittorio once again. It's very, very late where he is.
Yeah.
And he is gave us a fantastic, energetic talk tonight, and I really appreciate it.
Thank you. I appreciate you for inviting me. Was pretty fun, and I think I can go to bed now. And if you have any other question that pops up in your head, always open for chatting. I love C++. I love arguing about C++. So just find me, send me an email, a tweet, whatever, and we can chat about this stuff. Cool. Thanks everybody. Really appreciate being here.